Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're happy to have Prasad Raghavendra from across the lake, who will teaching us on approximating the optimum efficient algorithms and their limits.
Thank you. Okay, so let's start right away with looking at the max 3-SAT problem. So here you're given a 3CNF formula and you want to find an assignment that satisfies the maximum number of clauses. Now, it's a very well-known theorem that this problem is NP-hard. And as it turns out, most problems, optimization problems which we want to solve are actually NP-hard. So really, we want to cope with this. And one way to do that would be to say, okay, can we find a solution that is, say, at least half as good as the optimum? And that's the approach which led to approximation algorithms. So an algorithm is an alpha approximation if for every instance of that problem, it always outputs a solution which is at least alpha times the optimum. Okay, so that's approximation algorithms, and there's a vast literature on this area. However, despite this vast literature in the area, if you look at the core of most approximation algorithms, there are very few tools available. In fact, till 1994, nearly every approximation algorithm directly or indirectly relied on linear programming relaxations. And in 1994, Gomans and Williamson introduced semi-definite programming based algorithm for Maxcut. And semi-definite programming is a generalization of linear programming, so which makes it the strongest tool that we have today in approximation algorithms. So as of today, if you write a semi-definite programming relaxation and it does not give a good approximation, pretty much there is no way to get around it. So this is the state of the art, but before I go any further, let me define what are called constraint satisfaction problems. So max 3-SAT was an example of a constraint satisfaction problem. In general, what you have is you have a bunch of variables, and these variables take values in some finite domain, in our case Boolean domain, and then there are constraints on these variables. In our case, it is in max 3-SAT, it's just clauses. And depending on the kind of constraints that you permit, you get different CSPs. And depending on the CSP, its behavior depends on the kind of constraints that you permit. So since SDP was introduced, there have been lots and lots of algorithms for different CSPs using semi-definite programming. So I basically listed nearly every algorithm which has been there. So these bars should ideally indicate the approximation ratio, and it's a number between 0 and 1, but it's not completely drawn to scale, so at least the order is right. Okay, so these are all the algorithms. And in some cases, we actually know that you can't do any better. For instance, if you look at max 3-SAT, we have a NP hardness result which says that you cannot do better than 7/8 approximation for max 3-SAT. So that basically closes the problem for max 3-SAT because we have an approximation algorithm and a hardness result saying we can't do any better. But still there is gap for some very fundamental problems like Maxcut. For Maxcut, the best algorithm achieves a ratio of 0.878 approximation, whereas the hardness factor is 0.941. So there could be a better algorithm, or it could be that we could show a hardness of 0.878. So there is this gap in our understanding of this CSP.
Isn't the hardness result relying on the unique games?
Oh, yeah, that's what I'm coming to, yeah. So this is NP hardness and this is the algorithm, yeah. So, okay. So to deal with this gap, Subhash Court suggested that we work with a conjecture, a hardness assumption called the Unique Games Conjecture. Basically, Unique Games is the following problem. You are given a bunch of linear equations, modulo a prime p or a number p, and each equation is of the form xi minus xj is equal to cij mod p. So each equation has just two variables per equation. And what you want to do is you want to satisfy the maximum number of these equations. And Unique Games Conjecture asserts that given a system which is nearly satisfiable, if the prime is large enough, it is NP hard to satisfy even epsilon fraction of the equations. So given 1 minus epsilon satisfiable system, it's NP hard to satisfy even epsilon fraction of the equations. So this is the Unique Games Conjecture. It means that there is a solution which satisfies 1 minus epsilon fraction of the equation.
Only for linear, for this kind of system?
For this kind of linear systems. So this is the Unique Games Conjecture, and it's a notorious open problem today. There is no consensus either way about its truth or falsitude. And in fact, there have been several attempts to disprove the conjecture, and we are not even close to doing anything about proving the conjecture. In fact, this algorithm of Charikar-Makarshev, which actually gets to this is an algorithm for Unique Games Conjecture, and gets very close to disproving the conjecture in the sense that any improvement on this approximation ratio would disprove the conjecture. But it's not obvious that you could improve this approximation ratio either. So.
Number of equations.
N?
N.
Oh, here?
Yeah.
Oh, here n is the number of variables. All the equations, since they're polynomial factors, so polynomially related. Okay.
On 1 minus epsilon system,
Yeah.
spell out what the table means.
Oh, the table means that given a system of Unique Games problem in which is 1 minus epsilon satisfiable, this algorithm will output a solution which is 1 over p to the epsilon, a solution which satisfies so many equations. And p is the prime with respect to which the Unique Games problem is. This is a fraction of equations. So 1 minus epsilon fraction of equations are satisfiable. However, it only finds a solution which is which satisfies 1 over p to the epsilon fraction of the equation.
In the other lines, you have things that are close to 1.
Actually, they're they're close to 1 only if epsilon is small enough in these cases. In the original version of Unique Games, epsilon is a constant. So these algorithms are actually not, these two algorithms only work when epsilon is really small, and it doesn't have much to do. In the last line, lambda is the spectral gap of the Unique Games graph. So if the graph of Unique Games has a large spectral gap, then there's a good solution. Okay, so now we assume the Unique Games conjecture, and there are several hardness results which have been shown assuming the Unique Games conjecture. So the green bars indicate the hardness results. And the surprising fact is that if you look at Maxcut or Max2sat,
what does the approximation here mean? It's supposed to represent some number, right?
Yeah.
So what does this number up there of Unique Game mean?
So
It is approximated by a constant, right?
So this is the approximation algorithm. The blue bars are the approximation algorithms that we have, which is, it's a number between 0 and 1. What is the approximation ratio you can achieve? These are the NP hardness results which prohibit.
What is the number specifically for unique games?
For unique games.
Yes.
Oh.
You have epsilon and 1 minus epsilon. What is the number?
For unique games, it is 1 over p to the epsilon.
What?
The number which I showed, it is 1 over p to the epsilon. This is the best possible approximation.
Okay.
Assuming unique. That's the best possible known approximation.
But you're putting the constant bar there on the next chart. That's why.
That's why I said it's not. Yeah, this is not drawn to scale. Because I couldn't draw 1 over p to the epsilon. Yeah. So, but the surprising fact is that if you look at Maxcut or Max2SAT, the unique games hardness exactly matches the approximation given by the SDP. So for Maxcut, it tells you that you cannot approximate better than 0.878, which is exactly equal to the approximation given by the SDP. So this was kind of a connection which was somewhat mysterious, and it was believed that indeed there is some connection between unique games and SDPs. And earlier last year, which we showed the following result, that if you assume the unique games conjecture, then in fact for every constraint satisfaction problem, the simplest SDPs give the best approximation, computable efficiently. That is, it's NP hard to compute an approximation better than the simple SDP. So in fact, for all the CSPs, you have exactly a common barrier, which is the simple SDP gives the best approximation, if you assume the unique games conjecture. And surprisingly, the same hardness reduction also gives an algorithm which is optimal for every CSP, in the sense that it achieves exactly the approximation ratio which unique games tells you is optimal. So if one believes in the unique games conjecture, these two results would give both an algorithm which is optimal and hardness which is matching.
You just have to prove the conjecture.
Luckily, we are not.
You should directly look at the NP equal to P problem. That's just margin.
Luckily, we are not yet done, and we still have work to do.
So did you use the specific properties of semi-definite program, or this would remain true if you try more general programs like coding programs?
It uses properties of semi-definite program as well.
Okay. So it's possible for somebody to write a coding program and go beyond this?
If unique games is false, yeah. So this actually goes beyond CSPs, and there are other problems for which similar things happen. Like if you look at the three-way cut problem, here you're given a graph and you're given 3 terminals, A, B, C, and the goal is to actually cut the graph into 3 pieces so that you minimize the number of crossing edges. So that is the three-way cut problem. So it's basically a generalization of the classic ST cut problem, where you just have 2 terminals and you want to find the minimum cut separating them. This has a very nice approximation algorithm which embeds this graph into a simplex and cuts the simplex, and it achieves a 12 by 11 approximation for this problem actually. So this is a minimization problem, unlike our CSP, and there are several generalizations of this problem like k-way cut, zero extension, and there is this class of metric labeling problems. And it turns out that if you assume the unique games conjecture, for each of these problems there is a single linear program which gives the best approximation. This linear program actually has been used in one of these Chekuri, Kannan, or Gaussian, and this is the case.
Which node?
This is Cephi now. Okay, so that is about graph labeling, and it goes more. So suppose you have a bunch of football teams which play a bunch of games, and you want to rank the teams such that the result agrees with the maximum number of games. That is, in maximum number of games, the higher ranked team wins. Formally, this is just you're given a directed graph, and you want to order the vertices so that maximum number of edges go in the forward direction. So this is called the maximum acyclic subgraph problem, and this is in very old problem in approximation. And the best approximation algorithm we know today is output or random ordering, which achieves a half approximation. So a half approximation just because of yeah. Even that's even simpler. Pick an arbitrary ordering and output this way or the reverse. One of them will give more than half. So this is the best approximation we have today. And if you assume the unique games conjecture, indeed this is the best you can do. And in fact, it's more general in the sense that you can look at other kinds of ordering constraint satisfaction problems where your output has to be an ordering and there are constraints on that ordering. One can show that the simplest semi-definite program gives the best approximation.
So the best algorithm, there'll be some bad instance where it will achieve 1/2, but it's possible that you could have an algorithm that will be better than random in almost all instances.
Yeah.
It's analysis.
Yeah, it's a worst case analysis. Yeah. So actually, this goes on and on. So if you look at so there's this problem called the Grothendieck problem, which is just a kind of a special case of a quadratic optimization. Even there, the simplest STP gives the best approximation. And recently, Kortenauer pointed out that a class of clustering problems known as the kernel clustering problems, for them, simplest SDP again gives the best approximation. Huh?
That was the south, yeah.
Asaf.
Learn from the point.
Oh, there are 3 now, right? Oh, I forgot. Yeah, so really for surprising variety of problems like CSPs, labeling problems, some clustering problems, ordering CSPs, we have actually reached a common barrier, unique games, in the sense that all our algorithmic techniques have reached this common barrier on so many different problems. And this barrier, in fact, identifies exactly how well we can do today, in the sense that it matches the approximations of so many different algorithms. And if unique games is true, then clearly, that would, solve many of these problems in the sense that it would give a tight upper bound for all these problems. If unique games is false, then hopefully a new algorithmic technique will come up. Yeah.
So when you talk about the simplest SDP, you don't care. The rounding is. You look at only the quality gap. In the gap node, and the rounding is not important.
Yeah. Right. But for CSPs, we get a rounding scheme also out of this. But in general, I'm just talking about not the rounding, but just the integrity gap. And even if unique games is false, all this effort at proving results assuming unique games is actually useful because firstly, the algorithm which we obtained, generic algorithm for every CSP, it's at least as good as all known algorithms. I mean, it's a common algorithm which is at least as good as all the algorithms we know, irrespective of the truth of unique games conjecture. So, and
this is good in the approximation ratio, but is it also good in complexity or?
approximation.
They're all polynomial, but is it the same complexity as every one of the algorithms for every one of the?
So all the CSP algorithms I showed will first solve a semi-definite program, and then it would do a rounding. Rounding is usually linear time, and semi-definite program solving. Here again, even for the generic algorithm, SDPs take the same time. The rounding again takes linear time, except that the constant in that is horrible. That's the difference here. I mean, on the way you also get lower bounds against SDPs, that is SDP integrality gaps for several problems in this exercise actually. An interesting consequence of these reductions is that one can actually get an algorithm to compute the SDP integrality gap. So I'll give an example of an application. So the Grothendieck inequality is an inequality which is shown by Grothendieck in 1953, which holds for all matrices. Basically, it says that if you look at summation aij xi yj, and you optimize this over -1, 1, or xi yj being unit vectors, the two are related by at most a constant kg. Clearly, I mean, even without the constant, this side is better than this because when you are optimizing over vectors, you can also choose 1 minus 1 as your. And
There's no graph.
oh, there's no graph. This is just G for Grothendieck. Yeah. Yeah. So this is the Grothendieck inequality, and its value is unknown in the sense that these are the best upper and lower bounds that we have for the Grothendieck inequality as of today, and this work actually gives an algorithm to compute the Grothendieck constant up to any approximation in time which is doubly exponential in the approximation. Yeah. Huh?
So what's the new estimate that was obtained before?
Oh, we didn't. We couldn't even implement this.
Not even for 2 digits?
Huh?
Not even for 2 digits?
It's doubly exponential. So even if you get 2 to the 2 to the 1 over 10, 2 to the 2 to the 10, that's a large quantity.
Maybe you can start a project at SAT or something.
Yeah.
2 to the 1,000? You need first SETI to succeed, and then you need on all the galaxies before you.
Yeah. Okay, so this is. Okay. So now I'll move on to how one proves this for the case of Maxcut, which is a very simple case and which illustrates most of the main ideas in this. So Maxcut. So you're given a weighted graph, and you want to find a cut which cuts the maximum number of the edges, or you want to maximize the total weight of crossing edges. And we'll always assume that the total weight of the edges in the graph is 1. So it's a probability distribution over edges, and hence we can talk of just the fraction of crossing edges for every graph instead of the number. So one can write a quadratic program for this. Basically, for every vertex, you have a variable which takes 1 or -1 values, depending on which side of the cut it is. And I mean, this is just 1 if the or on different side of the cut. And you can't solve this quadratic program, so you relax this in the sense that you, instead of allowing xi to be 1 -1, you allow it to be unit vectors. So now you have this semi-definite program where vi's are unit vectors and we want to maximize this quantity. So, okay. So in terms of words, it's just that we want to embed the graph on n vertices into an n-dimensional unit ball while maximizing the average squared distance, average squared length of the edges, where the average is just the under the distribution given by the weights. So this is just restatement of Maxcut testing. Okay, so what is our goal? So we solved the semi-definite program and we got a bunch of vertices on the n-dimensional unit ball, and we want to find a maximum cut of this graph. And what we want to do is actually we want to get both the algorithm and the hardness at the same time. We want to get an algorithm and we want to show that it's optimal, both at the same time. Okay. So for this, we need, for hardness results, we need gadgets. And these gadgets are called dictatorship tests. So in this case, I would just introduce what I mean by dictatorship test for the special case of Maxcut. So for Maxcut, a dictatorship test is just the following. So a dictatorship test would just be a graph on the hypercube. So the hypercube is -1, 1. Let's say fix some large constant dimension, let's say 100 dimensions, and look at the hypercube in 100 dimensions. A dictatorship test is just a graph on this hypercube, that is with vertices being this. And it has what is called it should have a dichotomy of cuts. So if you look at the cuts which are parallel to the axis, that is the dictator cuts, they should have a high value. That is, they should cut a large number of edges. Whereas if you look at cuts which are far from every dictator, they should cut a small number of edges. And this is, the completeness is just the number of fraction of edges cut by dictator cuts parallel to the axis. And soundness is the maximum fraction of edges cut by something far from a dictator. So we want to actually construct graphs on the hypercube such that dictator cuts have very high value and things cuts far from dictator have very low value. So that's the goal. And suppose we do that. Suppose we construct a dictatorship test with completeness C and soundness S, then by result of Coate-Kindler, Mossel, O'Donnell, you immediately get a unique games hardness. That is, with the same parameters. So you would get a hardness saying that on instances with value C, it is NP hard to output a solution of value more than S. So, okay, so now we want to construct these graph on the hypercube. So what we'll actually do is the following. Suppose we are given some arbitrary graph on n vertices. We solved the SDP, we got the vertices on the unit ball. What we'll do is we'll use this to construct a graph on the hypercube with the following properties. If you look at a dictator cut, its value is equal to the SDP value of the graph G. And if you look at a cut which is far from dictator, so suppose this is a cut which is far from dictator for this 100-dimensional hypercube, then there is an efficient procedure by which you can get back a cut to the original graph with the same value. So if the graph, for instance, had SDP solution 0.9 while actual cut is at most 0.7, then what would happen is the completeness would be 0.9 because the dictator cuts would get SDP value, whereas anything not a dictator, if it cannot be more than 0.7 because you can, whatever the cut value is, you can get back a cut to the original graph with the same value. So, this actually already gives an algorithm for Maxcut in the following sense. So let's say we construct this hypercube. We can look at all possible cuts which are not dictators here, and run this conversion to get a cut of that graph. So run round on every cut which is far from a dictator on this. You get a cut for the original graph, and then you output the best.
So there is a huge constant because you have to look at all possible cuts of 100 dimensions.
Yeah, of the hypercube. Yeah. Actually, that is the reason why it's, and you might not have to look at all possible cuts, but in general for an arbitrary CSP you have to. Like maybe for Maxcut you can show that use half spaces or symmetric functions and so on. Yeah. So what we have done is we'll construct a dictatorship test with completeness SDP value, and the soundness by definition is the output of the algorithm. The optimal algorithm which I showed. So using that conversion, you would get a fact that the algorithm is indeed optimal under UGC. Okay, so this is the hardness. This is what so now our goal is just to do this conversion. From a graph, we want to get a graph on the hypercube with these properties. Okay, so let's see how we construct this. So we have a SDP solution. We want to construct a graph here. So at an intuitive level, what we are going to do is just the following. For every edge E here, you connect every pair of vertices on the hypercube at that distance. So if the E is of length D, then you connect every pair of vertices of length D on the hypercube. So, but this is only roughly because we are talking 100-dimensional hypercube, and there might not be any edges of that length on the 100-dimensional hypercube, starting from the SDP solution. So really what we do is I'll describe a random procedure to sample an edge from the hypercube that would give a graph on the hypercube. So what is the random procedure? You basically pick an edge from the original SDP, arbitrary edge UV, and then you generate edges of that length on the hypercube. How do you do that? You pick a random point, and suppose the length of the edge is D, then once you pick the random point X, you flip every bit of X with probability D over 4 to get another point Y, and connect these two. So really the expected length of the edge XY will be equal to D, because you are flipping each bit with probability D over 4. So actually, let's ignore that now. And then once you generate this x and y pair on the hypercube, we actually perturb each bit of x and y by epsilon with probability epsilon. We can ignore this fact for most of the talk.
Since x is random, why do you bother to perturb it? It's as random, unperturbed as perturbed. See, y has to be perturbed, not yx.
It would give the same graph, yes, but this is just easier for analysis. Just for analysis, it's easy. Yeah, and then you output the edge x prime y prime. So this gives a graph on the hypercube because I'm giving you a method to sample edges of the hypercube. Okay. So let's see how dictator cuts do on this. So, okay. How do we estimate the value of the cut? The value of the cut is given by, first we chose an edge E in the original graph. So expectation over the choice of the edge E in the original graph. And then we generated these 2 points on the hypercube with the appropriate distance. So expectation over the choice of edge E and expectation of the choice of these 2 points of, suppose f is the cut, which is, a cut is a function on the hypercube, which is all outputs 1 or minus 1, f of x minus f of y whole square. This is just an indicator for whether the edge is cut. So this is just an expectation giving out whether this particular edge is cut or not. Okay, so now we'll set f of x is equal to x1. That is the first dictator function. Okay. Now, the point is our choice of these 2 points x and y is such that x1 is not equal to y1 with exactly the probability u minus v whole square. If E is the edge uv, we pick an edge uv, we generate edges of exactly that length on the hypercube. So x1 is not equal to y1 with probability u minus v whole square. So we replace that here. And you can see that this is indeed the SDP value of the original graph, because expectation of the choice of edge E of the length of the square length of the edge is just the SDP value. So dictator cuts get the SDP value. So now we want to analyze things which are not dictators, cuts which are not dictators. And to do this, we define a graph on the Gaussian space. So the graph is as follows. First, I'll define a random projection of G. So random projection of G would be, you obtain random projection as follows. You just generate 100 random directions in the Gaussian, in the 100 random vectors, each component being IID Gaussian. You project your SDP solution along these 100 directions. So each vector u, you map it to u dot g1, u dot g2, u dot g100. So this actually, if you start with a graph in n-dimensional space, it gives you a copy of the graph in 100-dimensional space, because you just projected it down. So there is again a perturbation, but let's ignore that for now. So this is the copy of the original graph in 100-dimensional space. And the real Gaussian graph is just the union of all possible projections of G. So you take, for different choices of the random vectors, you have different projections. You take the union of all possible projections, that is the Gaussian graph. So it's a graph on real numbers to the power 100, or 100-dimensional space, and it's a, The nice thing about this graph is that suppose somebody gives a cut for this Gaussian graph then one can get back a cut for the original graph. How? Just by, this Gaussian graph is just union of several copies of the original graph G, but placed at different places. So you pick a random copy and read out the cut. So basically you pick a random projection and then you read out the cut. That would give a cut for the original graph. So this Gaussian graph, given any cut, we can get by a cut for the original graph. And what we will do is, we have the hypercube. We have a cut which is far from dictator on the hypercube. We will use the invariance principle to say that there is a cut of the same value on the Gaussian graph. That would finish the proof. So the invariance principle is a generalization of the central limit theorem. So central limit theorem very roughly says that sum of large number of 1 minus 1 random variables has similar distribution as sum of large number of Gaussian random variables. And the invariance principle for low degree polynomial says that you replace the sum by a low degree polynomial. If a low degree polynomial is far from every dictator, then you substitute 1 minus 1 or Gaussian, it has similar distribution. So, okay, so what do we have now? On the hypercube, we have a cut which is far from a dictator. So it's a function on the hypercube. So express it as a multilinear polynomial, as a Fourier expansion. And now you start plugging in Gaussian values. Ideally, you would expect it to output just real numbers. But because of the invariance principle, you can assume it outputs 1 minus 1 values. Because its behavior on the hypercube is same as behavior on the Gaussian space. So you substitute Gaussian also, it outputs 1 minus 1 values. So really, the same polynomial also gives a cut of the Gaussian space. So we use an invariance principle one more time to actually say that if you give me a cut which is far from dictator on the hypercube, the corresponding polynomial extension is a cut on this Gaussian space, Gaussian graph, with the same value. So we use the invariance principle to show that the Maxcut value is the same on this Gaussian graph as the hypercube graph. And that kind of finishes it, because basically all we have shown is that given a cut far from dictator here, you can get a cut with the same value on the Gaussian graph. And we already saw that Gaussian graph is, given a cut for the Gaussian graph, you can get by a cut for the original graph, because the Gaussian graph was just a union of several copies of the G. Okay, so that kind of finishes the proof. So this same framework works for all CSPs, in fact, and it's kind of a powerful tool to convert the weakness of an algorithm into unique games hardness results. Okay, I'll get to future work now. So of course, the most important question is to actually resolve the unique games conjecture, and but since there are probably more tractable goals which one can work on. One is that we said that if unique games is false, it will hopefully lead to new algorithms. It's very good to make this precise in the sense that if unique games is false, show that it actually leads to some new better approximation for a problem which we care about, like let's say Maxcut. The other is, this is a very pressing question, is that we should at least show that stronger semi-definite programming relaxations do not already disprove the unique games conjecture. That is, to go beyond this barrier, do we have to look beyond SDPs, or even just stronger SDPs would do? Even this is unresolved today. So it could be that just a few more constraints into the SDP would give a better algorithm for these problems, and we haven't ruled that out yet. And the other interesting open direction is that there seems to be some connection between unique games and expansion, in the sense that all hard instances of unique games actually come from graphs in which every small set expands. So in fact, the hardness of unique games actually comes from just expansion of small sets in the Gaussian space. But at the same time, recent research shows that if your graph is an expander, then unique games is easy. So these seem to be contradictory, and it needs to be resolved actually. And of course, one needs to look beyond CSPs. All the SDPs came in '94. There have been very few algorithms for problems like which are do not look like CSPs, like metric TSP or Steiner tree, or there haven't been any applications of SDP or unique games for these things. And it will be interesting to see if techniques are useful there. This is an interesting.
From SDP point of view,
vertex curve. Yeah.
Results came out from it.
Yeah.
So that's it.
Vertex curve is one. Yeah, one of the things. Yeah. Yeah, but it still is almost a CSP in the sense vertex cover.
Huh? For vertex curves is a UGC hardness of
Yeah. True. But it's not. Although LP still gives the best approximation, it's nearly a CSP. In fact, it fits in. One can show vertex cover hardness using this framework in this paper. However, these things are way out of the reach. So there's this fairly 15-year-old conjecture that every CSP is actually polynomial time solvable or NP hard, which means that 3-SAT is NP hard, 2-SAT is polynomial time, and there's nothing in between. Every CSP is actually polytime or NP hard, and this has been resolved for Boolean CSPs and CSPs over domain size 3, but higher order it's not been resolved. And it recently Kuhn and Schlegedi have pointed out that some of these techniques from approximation can be useful to resolve this. Okay, so I'll conclude the talk here. I would be happy to talk about any of the other things which I was interested in. I am interested in at some. Yeah. Okay. Thank you.